All right, we're live. Good. So where was I? Right. So it's my pleasure to introduce Maria Tikhanovskaya. Maria is one of a number of Subir Sachdev's graduate students, many of whom happen to be graduating this year, and I think you're one of those, right? She did her undergrad in Moscow, and in the Academy of Sciences, although I don't know is that the right name for the
Yeah,
institute?
so I did my thesis in Stiklov Mathematical Institute of Russian Academy of Sciences, but I did my studies in a Moscow Engineering and Physics Institute.
Uh-huh. I'm not very familiar with these institutes, but
No problem.
but she did a lot of work there, and she published 5 papers, which are all on topics related to SYK. It seemed to me, but I couldn't quite. I didn't read them in depth. And then she's went to Harvard, and she's been working on strange metals, and there's some more SYK work, if I understand it. And these are like strange metals are a topic very I think we're pretty interested in this group. Today she's going to tell us about spin glasses. We are also interested in like spin liquids and things like that. But I have not yet got a firm grasp of really what a quantum spin glass is. So I'm really looking forward to today's talk. I thought when I saw how fundamental this research was, it seemed to be a good topic for us to all learn a lot. So, well, without further ado, let me turn it over to Maria.
Thank you so much for such a nice introduction. Really happy to give a talk here and being live streamed. Interesting. Anyway, so yeah, today I'm going to tell you about spin glasses, the work that we just recently posted in archive this month with Subir and Ryan. Ryan is a postdoc, I think PCTS postdoc at Princeton, and Subir is my advisor. Yeah, so this project was going on for a few months, and I just started learning about spin glasses, well, since they started the project. So I'm still like trying to figure things out, but yeah, it seems like it's a very fascinating topic with like lots of history. So I'm going to tell you something that I know about it, but definitely there's so much more that I still don't know. All right, anyway. Yeah, so here's the outline of my talk. I'm going to tell you about the definition, how we define the spin glasses, and I'm going to explain a little bit why they're interesting, why we should care about them. Then I'm going to tell you a little bit about background, because in order to understand, the essence of them, we need to know, some fundamental things. And I'm going to tell you about our results on quantumizing spin glass and the biggest 3 rotor spin glass, and what's cool about them. And then let's just conclude and give you the outlook. All right, so let's first define the spin glass. Spin glass in condensed matter literature is defined as a magnetic state with randomness and frustration, which is essentially a mixture of non-magnetic host metal and small fraction of magnetic atoms. So you dope your non-host metal with magnetic ions, and essentially what you get at low enough temperature, you get the fact that spin starts freezing, and this freezing is happening in a very complicated random configuration. So imagine like at very small temperature, you can end up in a ferromagnet and like metal. But sometimes if you have your non-magnetic host metals with the magnetic atoms, then you end up in this like very weird configuration. And that all happens because you have both frustration and you have a disorder in your system. So another way to look at them is look at out of equilibrium dynamics of the systems. So imagine you initialize your system in some state, and then you wait for some time, and then you start measuring correlation function. So the C is essentially that. So it's 2-time correlation function. And what you actually see is that if you wait for long enough time, your correlation function starts saturating to some value. which means that you essentially break ergodicity. So your system does not explore the whole phase space, right? So and it just gets stuck into like one of the minimum that I'm going to tell a little more about. So in these curves is essentially if you don't wait for long enough time, then you don't reach that equilibrium state. So your correlation functions like slow decay to actually to zero. Yeah.
Can you give us a sense of, so you have a 2-time correlation function, but you're plotting with effect of 1 parameter. So can you so how do you, why is this the way to think about a 2-time correlation function?
So this is 2-time correlation function because so you have 2 spins, right? One spin depends on this time, the other spin depends on this time, and you can vary both. You can just like in easy. So it's hard to write. It's hard to like plot a function with 2 times, right? You want effectively 1 time.
You can plot an image or something like that, but.
Yeah, but yes, exactly. But it's just a little bit more natural to think about it as you wait, you initialize your system in some state, and then you wait for some time, and at that time you start measuring the correlation function.
So T sub W is T weight. Is that
exactly? It's T weight. Yeah. Yeah. And if you wait for long enough time, then you can actually potentially reach equilibrium. And equilibrium, what it's called, is the plateau of this correlation function.
I see. So in real materials, that long time is still reasonable, or for spin glasses?
It's actually very long.
It's very long. Okay.
Yeah, it's very long. So
and they don't all asymptotically approach zero?
That's the okay. So it's a good question because we still don't really know. We don't know if the classical computers essentially can reach that value if we can wait for such long time to like reach that value, or it actually will all go to zero. Yeah. But we believe it should be the case. Okay, so let me just talk a little bit about why they're interesting. It always depends on who you ask. So if you ask a person with a CS background or a quantum information background, they will probably tell you that they're tightly connected to the optimization problem. So imagine you have the interaction between 2 spins, SISJ with JIJ, and these JIJ couplings are random and like Gaussian distributed, whatever. So the question is how to find this ground state. So since this spins are quantum, you have configuration of n spins, and so you have spins up and down, and you have 2 to the n configuration of n spins. And essentially, to optimize this problem or to find like the optimal minimum, this is called so-called NP-hard problem. So classical computer just cannot solve it, right? In principle. And which, it's just essentially what it means is that there's no known algorithm that can find the ground state on a classical computer with time growing as a power of n, right? So for small system sizes we can find, but like in thermodynamic limit we cannot. And the question from the quantum point of view is there a quantum algorithm that can solve this faster, or like find the ground state a little bit faster than classical computer, or like linearly with n, which would be awesome, but we don't know that. So that would be the quantum.
You're talking about a classical spin, is that right? Like this a classical spin, but the quantum question is, can I still find a walk through Hilbert space that might be better than
then you would do
a walk through the classical states of a client that you would have to do
up and down.
Classical computer.
Yeah, essentially, yeah. So this is the review that talks a little bit about that. Then from the condensed matter point of view, which I'm most excited about, is the fact that the spin glassiness effectively doesn't exist in nature, so you need to somehow initiate it. But it turns out that some people think that this can be a phase in high temperature superconducting phase diagram. So in cuprates, so if you have whole dot cuprates, then apparently people saw some signatures. If you get rid of superconductivity, apply a huge magnetic field, then at small enough doping, you will see this like spin glass dome. But we don't necessarily, like, we don't have a theory obviously of that, so we don't know if that's actually spin glass, but people think that they see some signatures of it. So that would be interesting to study in this context. Then another important question is these features, spin glass features, arise due to disorder and frustration. So long relaxation time, a rough energy landscape, and microscopic degeneracy of ground state. There is essentially so much that is encoded in them. So it's hard to find a system that like has so much structure, right? So it has some weird order at low enough temperatures. When you have disorder and frustrations, you pretty much have no symmetries in their system. Important question is just how, what is the mechanism for spin glass order in finite dimensional systems? So what I'm going to be talking about is infinite dimensional systems and mean field spin glasses, which means that there is no notion of space at all. They all all the spins talk to each other all the time. So for finite dimensional systems, though, like a real spin glass, like 3-dimensional, for example, we actually don't know the mechanism for how they arise, and nobody knows that. So people have some conjectures, but it's pretty much impossible to prove at this point. So that's the question that is very much unsolved. So other perspectives would tell you, other people would tell you that spin glasses are also very interesting. So for example, from neural networks point of view, spin glasses provide a very comprehensive mathematical model when the network size approaches to infinity. So people use a lot of technology from spin glasses to describe that. Also in biology, apparently protein folding uses some techniques from spin glasses. And even in economics, I recently found this review that people use spin glasses to describe some network games, large random economies, and apparently it works. So that's pretty interesting. And yeah, so people are very excited, especially recently, as you can see, it's like all this year's papers. So what are the challenges? Why is it so hard to study spin glasses? And it's been like that for a long time, since like 80s. People had a hard time studying them. So due to the long relaxation time and the degeneracy of the ground state, it's very hard to find a numerical instrument to study them. So people these days use deep learning to do that, but I'm not familiar with that much, so I'm not exactly sure, but I know that there is a recent progress in that regard. Then another challenge is the ergodicity breaking, and which is related to long relaxation times. So it just essentially means it's just really hard to achieve thermal equilibrium. So it's really hard to achieve the equilibrium state and then, say something about the phase of matter per se. So what that means is that the energy remembers the information about the initial state, and it just doesn't forget about it after a long time. And the important last one is that it's just really hard to simulate, which goes back to the first point. But what's even harder is that imagine that you came up with a theory for spin glasses. If you cannot simulate them, then how are you going to compare your results with? So what's going to be able to prove that your theory is correct? So all of this is just making this problem really, really hard, but really interesting at the same time. So what are the approaches to study spin glasses? As I already said, the deep learning methods. So this paper from 2022 I found that says something about that, if you're interested. Monte Carlo method is one of the best approaches these days because it's the randomness is already encoded in the method. And you can generate, but in order to achieve the equilibrium, you have to generate lots of states. And that's very challenging. From the theory point of view, we use the method so-called large N expansion. This is for equilibrium techniques. For out of equilibrium techniques, we use Schwinger-Keldysh techniques, and for equilibrium, we use replica symmetry breaking, and there are other techniques like droplet model, droplet model to finite and infinite dimensional spin glasses and so on.
Question.
Mark,
oh, you have a question? Go ahead.
I do have a question. Yeah. Is with your theory approach, do you run into the sign problem at all? Because in the Monte Carlo method, you would, I think, it would absolutely run into the sign problem. but does the
Mhm.
large n expansion and the Schwinger-Keldysh problem run into sign problems?
No, no, there's no same problem. There is not like numerical simulation there. You just there's like a mean field method that you start with your free energy and then you minimize it like using just you know, pen and paper.
Oh, okay, okay.
And then you like end up with some equations self-consistently that you can solve. You can solve like self-consistently, and that's
Oh, okay. I see.
yeah. Yeah.
So my question was, are there fancy Monte Carlo methods that people use just to, like you can imagine the simplest one is you flip a spin up to down.
Right.
That's probably hard. That's probably,
Right.
very slow, but I wonder if there are fancier ones where you look for clusters, or do these things, I don't know.
I'm trying to think of I'm sure there are. I've never worked with that, so I'm not exactly sure. People probably at Flatiron can say something more on that. So I don't know. Yeah. Okay. If there are no questions, let me go to the background knowledge a little bit. So what do we need to know to understand a little bit about spin glasses? So first, as I said, it's in principle, we believe it's a phase of matter. Therefore, there should be some order parameter that describes it. So we'll talk a little bit about that, and I will talk about ultrametric structure to understand this order parameter. I will also talk about the p-rotor model as it's one of the simplest models to see how this technique works. And I will also talk about replica symmetry breaking, the equilibrium approach to study these spin glasses. Okay, let me start with the replica trick. So this is just the first thing that we do when we study spin glasses. So in principle, so imagine that you have a random model. So you have Si as J, J, and JJ random. But you want to evaluate if the free energy somehow, right? You want to find like the minimum state. So in order to do that, you need to average over randomness, average over disorder somehow. So free energy is proportional to log Z. So one would think that we just need to average log Z, but this itself is really, really hard to study. So instead what we do so-called replica trick, where we just do this, we just do this limit of n goes to 0, but n is just some parameter, and doing 1 over n log Z to the power of n, and then average Z to the n. So therefore, we don't need to average log Z itself. We just need to average Z to the power of n. So this n is called replica. And that essentially means that we take our system and we replicate it many, many times. And then we have to take this n to 0 at some point. Yeah, so here, as you can see, n is a real number. So it's not integer, right? So we have to promote n to, in order to study this, we have to promote n to the integer number, just because we want to take the partition function and compute it somehow. And we only know how to do that if we have like integer number of the integrals, right? We don't know how to do it with like real numbers. So we promote n to the integer number first. We compute this partition function averaged. And then after we do that, then we want to take n to 0 limits, right? So then we promote it back to the real number and take n to 0 limit. So this is like a two-step process that one would think is very fishy. And sometimes it is, but sometimes you can actually prove that it works. And in the models that I'm going to show you today, it does work.
So there's an intermediate step where you take an analytic continuation of some kind.
Yeah, so the intermediate step where n is the integer number. So n is 1, 2, 3, 4, 5, 6, 7.
Right, but then after you've calculated this Z bar, Z to the n bar, you get it for a certain set integer values of n, but then you take those numbers and you try to construct a real function of n.
Exactly. Yeah.
Then you
exactly.
take after that.
And then you take n to 0. Yeah.
Isn't n naturally an integer though? Because since you're doing like a replication of Z, and Z is just a consequence of like the the random coupling on the sites SI and SCA? Or am I thinking about that wrong?
So this is like replication of the entire system, right? Well,
Right.
yeah.
But like, how do you replicate part of the system and not the whole system? Is what I meant by that. Like, isn't n being an integer means you're replicating the entire system?
It does, yeah.
So
Right, so-
thinking of the fractional value of n would be like replicating part of the system.
Right. So I was just kind of curious what the like why would is I guess maybe let me phrase that better. Is there any benefit to doing n not as an integer? As a real number.
Yeah, exactly. So this is how this limit in principle should work. So you can only like this is equality, right? So there is no approximation here between these two sides. But in order for this limit to work, n has to be like a real number.
Oh, okay.
I think you can try it on like simple functions and see that that should be the case.
Is it required to be a real number, or is it could it just be? I mean, integers are a subset of real numbers, so couldn't it just be? So isn't it true if it's true for real numbers? Isn't it also true for integers?
To get the average of log z, you need to take the limit n goes to 0. Right.
So okay, maybe yeah, I see the confusion. So maybe stepping away from the n to be real number. Another weird thing about this whole thing is imagine that you replicate your system n times, and then you somehow need to take n to 0. So what does it mean to have like number of replicate systems to be 0?
Right.
That's like a little bit different point than just having it to be a real number. But that's just what people usually say when they say like this is like a weird
Right,
thing.
right. And then you just okay. I guess it's just getting hung up on details. So restricting it to the integers seems really natural to me. So
okay, good. That's good. But actually, and the third thing that is actually strictly speaking might not be correct is that this limit just does not work for some functions. One can show, I think, on a sine function, something I don't remember, but yeah, this limit will just not work. And that's just not work for sometimes.
So here,
yeah.
Quick question. So here you are still like averaging over the disorder realizations. Are you like averaging over?
That's correct. Yeah.
So you, like for each like disorder realizations, you are like taking many copies and then letting like calculating this like partition function and then letting n to 0 eventually.
Yeah.
Okay. Thanks.
Yeah, and as I already mentioned, like, evaluating this is so much simpler, as you can see, than evaluating this like log z. Log is not good for us. Oh yeah, and everything that I'll be talking about for the next few slides is going to be from this review, and it's really nice. So if you're interested, definitely that's the way to learn about these things. All right, so now let's talk about order parameter a little bit. So when we consider just a simple Ising model, the order parameter would be magnetization. That system is just not disordered, right? And we can consider total average magnetization where we just average over spins, right? And we know that it should be 0 in high temperature phase, and it's going to be non-zero when the symmetry is broken. So there's a phase transition between, and you can capture it using this magnetization. Now, one would think that the natural order parameter for the disordered systems would be a similar thing, but just average over disorder, right? So that would be correct, except as I mentioned, when you go through the phase transition and you end up in a spinless phase, all your spins are disordered. So not disordered, also all your spins are frozen, but they're frozen in like weird configuration. And you cannot predict that, right? So it's not like ordered state, it's this, random configuration of spins. And therefore, when you take the average over all of it, you'll end up with 0. So therefore, this is just not a good order parameter. And people thought about it for a while, and they found the better order parameter, which is called Anderson order parameter. So that one is very similar, except you need to take the averaged over spin squared and then average over disorder. So what is this average? First of all, it's a thermal average. Yeah, so essentially what it means is that if your local magnetization is non-zero, then your spin cluster parameter is not going to be here as well. So one important thing to say about this order parameter is that the special case of something so-called overlap. And let me talk a little bit about this. So what is the overlap? Overlap is a function that is defined between two states. So imagine that you just consider like a regular phase space in classical physics. And imagine that your system does not explore the entire phase space. So you have some broken ergodicity. Then apparently what happens is that your Gibbs measure can be split into subcomponents. And then you can construct some pure state. So these states are pure states. Now, I'm not going to go into details of that. I'm just saying that essentially this function measures the overlap between pure states. Yeah, so this is how you can just write it down. So this averaged is, you can just take the path integral and compute the averaged over all configurations. Yeah, so it's similar here. And then you just compute the overlap. Like what does that function give you? If there is overlap, it's non-zero. If there's no overlap, it's just zero. And there's a thing called so-called self-overlap is when you just measure how the same state is overlapped with itself. And that's important information that will be good for spin classes as well. Yeah, so as it says here, the larger self-overlap is, the smaller the state. And the smaller self-overlap is, the broader the state is. Okay.
Quick question about this order parameter. So
Yeah.
I'm trying to understand how this parameter would distinguish between like a spin glass phase and a paramagnetic phase. Could you explain that?
Yeah. I'm going to connect the actual model of spin glass with this thing just in a second, and maybe we can talk a little bit more about that. Yeah.
Okay, sure.
So yeah, let me just focus on a simple model called P spin model. We call it in the paper P rotor model, and it's a spherical model. So what does that mean? So first of all, P spin means that you have P spin interaction. So you have P spins here, and they all interact with Jij, or in this case, Ji1 to Ip. And P is usually greater than 3 because P equals 2 is just the Ising case, right? So what does spherical mean? It means that you have a spherical constraint. So here in this model, sigmas are promoted to some real numbers. So it's not like up and down, it's actually some real number. And in order to confine your energy, we have to impose the spherical constraint, otherwise it's just going to diverge. Yeah, so this is a kind of weird model, but you can solve it analytically, and it gives us some intuition at least what's happening. So again, in order to solve this model, we need to compute the free energy. In order to compute the free energy, we need to average over disorder, right? So remember I told you that we need to take average of log z. So let's actually take average over, forget about log, and just take average over z, and then take it to the power of n, and then take an n to 0. Sorry, that's not going to work. No, okay, let's just average over z. Okay, so what happens if you average over z? You can actually compute it pretty easily, and that's going to be your answer. So what are we doing here? So we have the path integral over sigmas. This is our model. This beta is the temperature, inverse temperature, and this exponent is just how your couplings are distributed. So here we took P equals 3 first of all, and second we have a Gaussian distribution of this component. This is just normalization constants, and P should be 3 here, by the way. Yeah, anyway, so this is just averaging over disorder, and you can integrate JJs, and get this form and then integrate all the spins and get the actual analytical form of the partition function.
So is
Yeah.
is the p, does the p equals 3, is that the special, is your your exponent n beta squared over 4 omega, is that the p equals 3 case, or does p kind of disappear from this equation?
P is the parameter, P is like the model, right? So we just take P equals 3. So this should be this should be 3.
Right, but I mean, so in your final answer there on the very right hand side of the equation, there's no p anymore. So is that special? Yeah, is that special for p equals 3, or does p disappear from the equation?
So it will be contained in this omega.
Oh, okay.
Yeah. Mm-hmm. Yeah, you're right. So this is just a mixture of p equals 3, not 3. But yeah, in principle, it's all analytical. I think it should be contained in this omega. Right. So this is a simple answer for the partition function, very analytical, which is usually we obviously cannot do. Very interesting. It turns out that's actually not the correct way to do this thing. To do this, we have to take average, so-called quenched average. So how is it different from the annealed average that I showed in the previous slide? Is you first have to replicate your system n times and then take the average. So that turns out will make things much harder. In what way? So again, let's take our average over this order, but now we don't have just one term, we have n terms, right? Then after we integrate over this order, we have like this six spin interaction. And the good thing is that we can combine all of them and make it like single side action essentially. So you can just sum over all i's and have this essential product of so have product of 1, 2, and 3. So p or p in general, right? So p equals 3 here, but in general it can be p. So it seems pretty simple. What's the complication? The complication is A and B here. So A and B are replicas. That's what we did to the system. We replicated our system. And that turns out that it will make things much harder compared to this answer, right? Where it's just, simple number. So here we have some function and we need to deal with it somehow. So again, it turns out that the annealed solution has a higher free energy than the quenched solution. So quenched solution is the one that we have to ultimately do. But the good thing is that annealed solution actually corresponds to the paramagnetic solution, or like above the fixed transition point, we can do annealed average. Below the fixed transition point, we have to do quenched average. So this thing is.
Can you explain again? And so quenched, I guess maybe I'm always thinking that you have this disorder average you have to do. But is annealed and quenched, is that? I guess I just think of annealed as you came down slowly in temperature or something like that.
So annealed is essentially you fixed your coupling constant and you take an average, right? So I might be wrong in this situation, but imagine that you take a snapshot and you just do the average there. You take another snapshot, you do the average there. And that's how you construct your so essentially just take like average of one realization.
Are you building these averages up to make the whole system? Is that what
that's the annealed average.
Okay, right. That's what I was that's what I meant.
Yeah. So quenched average, you have to first replicate it and then take all the averages, right? Then take average of the whole thing.
Interesting. So in one sense, you take all these replicas and you quench it by sending n to 0. And the other annealed way, you take a bunch of snapshots of smaller pieces and then piece them together.
Yeah, but you have to average in each of them, right?
Oh, okay.
Yeah, that's the annealed one.
And the annealed one, just refresh my memory. The annealed one you said is not helpful, or it was
annealed turns out to be incorrect. Yeah.
Okay.
Yeah. So you have to do quenched for describing.
Z bar to the exponent n, whereas quenched is z n to the bar. Is that?
Exactly.
Oh.
So yeah, this is z n to the bar. This is quenched. Z n bar quenched, and this is the annealed z n.
I put that to the end.
But the problem that Maria said was if you take the z bar to the n, z bar to the n, then mathematically there's some issues with that, right? So instead it was more of
Doesn't
like
give
a
us the thing we want, right?
right.
But it magically works above the phase transition, so that sounds convenient.
Yeah, exactly. That's very convenient. It does work above the phase transition. Yeah.
So this
Actually,
annealed expression,
Mhm.
just trying to understand like the
Yeah.
statement that Michael was making. So the annealed expression makes sense like above the phase transition. Is that what the statement was?
Exactly.
see.
Annealed is the one that gives you the answer above the phase transition.
I
Which is
see.
nice. Yeah. At least in this model specifically.
Yeah, but like this expression seems kind of like a, I don't know, kind of like a trivial one, right? Like because you know it's like averaging over all disorder. I'm kind of thinking like in terms of like, you know, like density matrices. Like it's like, you know, like it's like taking like average of like different uh you know, taking an average of like different random states would give you some kind of like trivial, like, you know, maximally mixed density matrix, right? So this expression seems kind of yeah, kind of like trivial to me, like this annealed expression.
Wouldn't that kind of depend on what omega has inside of whether or not it's trivial? I mean, omega could be the complicated term here.
Yeah, but like why does it work like above the phase transition? Like, is there something like trivial going on like above the phase transition, which is why like this expression works?
Well, yeah. So above the phase transition, you have phase transition to paramagnet. That's kind of trivial.
Okay. So this expression can basically like explain a paramagnet, but not the spin glass.
Exactly.
I see.
Maybe that's connection to what you're thinking, but I'm not sure. Yeah.
Okay, yeah, we can move on.
Yeah.
Thanks.
Actually, 1 second. I think. Oh, right. So, okay. So if you do the annealed average, right? So if you have z bar and then you do to the power of n, then you just your n goes here, and then you have just like log z bar, right? Is that clear? Because yeah. So yeah, in principle.
Yeah. That's why the annealed that doesn't work for when you take n to 0, but it's like but the way you described it, it's much more of like a like an interpretation of z bar to the n than it is like a mathematical expression of z bar to the n.
Yeah. So annealed. So this is quenched. Annealed would be z bar to the n, and then you log something to the n. Just go like n goes here. This two cancel out, and you have just log z bar, right? So you log z the whole bar equals to log z bar. And that's a very special case. Only works for paramagnet usually. Yeah.
So I guess the weird thing about this is that when you get down to that certain, like when you get to the when you get down to the past the phase transition, then the spins sort of become locked in this like kind of random thing. So that's what makes the spin glass, and that's why the annealed is not working, and you have to use the quenched. Okay. Great.
Yeah, exactly.
Very interesting.
Okay. All right, so that's where we stopped. So we're doing quenched average, right? So that's our integral. Now what we do, we want to analyze this partition function somehow. In order to analyze it, we actually need to introduce Haber-Stonage fields. And essentially what we do, we just say that this thing is a QAB, and AB, again, replica indices. And this whole thing, we will connect it to the order parameter. So the connection, the overlap function that we just talked about, it appears here very naturally, with some with some things that that one needs to think about. And the self overlap here is just replace B with A, and you have sigma I A squared, and that's just our spherical constraint. Therefore, it's one. This just for this model specifically. Okay. All right. So let's move on with that. And as I just mentioned, so this is the overlap function that is going to be connected to our order parameter. And in order to decouple this model and somehow integrate spins out, we need to introduce a delta function, which is essentially, we're going to call this QAB the Haber-Stonage field. And what we get at the end is this kind of partition function. So we have now, instead of one integral, we introduce two more integrals, QAB and lambda AB and sigma IA. So if you dealt with mean field theories before, you are probably this is very familiar to you. But by introducing these two additional integrals, you can now integrate out the sigma fields. And now you just end up with some effective action, which is this S, that depends on this new introduced variables Q and lambda. And now the way to finally get the answer is to minimize this S, which is the saddle point, which just means we need to get the saddle point solutions. Yeah, so this is our action. After integrating spins out, so we just get this log determinant and we have this sums. It doesn't really matter, but yeah, we get this saddle point. We get this action, effective action, and now we can just take derivatives of it with respect to Q and lambda, and we can get two equations, and we can solve them self-consistently. They will depend on each other. Q lambda.
We need to send n to infinity for this approximation to work. Is that right? Capital N.
Yes, exactly.
Sending capital N to infinity.
Yep. Yeah, and it's supposed to be very large.
Making the saddle point approximation.
That's why it's called large N expansion, right? Because so yeah, we use saddle point method or steepest descent method to solve this problem. Right, so that's what we do. So this is our final free energy that we can write down and take n to 0 limit eventually. And this is QAB to the power of p is our order parameter. And this is one of the saddle point equations, by the way.
So capital N here is the system size. The number.
Essentially, yes.
Okay.
Yeah.
And this is hence the restriction why finite is much more challenging, because you don't have the saddle point approximation. Is that one of the reasons?
Exactly. So so for finite system sizes, what doesn't work is doing the from here to here.
Okay.
Yeah. Yeah, so you can't eventually end up in the like single site effective action. So it's in single site Hamiltonian. It's just not going to work. You have all sorts of complicated terms there, and it just all breaks down. So you can't analytically solve the model.
Oh, so that expression, sorry, has like a +1 over n or something, or this expression, this last line, approximation.
Yeah.
Happening for, so there's like factors of +1 over n in the exponential or something like that, plus order 1 over n or
this
right, the first term right there.
this one? Yeah, this 1 over n.
To go from the second last to make that equal sign, is that, I thought that was equal.
Yeah, they're equal. Yes.
They're equal. Okay, so you didn't make any approximation here.
Sorry. Yeah, there are no approximations here. Yeah. Wait. 1 sec. You're right. So yeah, there is no problem going from here to here, but there is an issue. Sorry. So you cannot. So if you take this over average, yeah, sorry, right. So that's right. If you have finite system size, this expression will modify. It will harder. So this is exact, but this is going to be different by itself. Yeah, after integrate out over this order. Yeah. So this simplification only because you have like all-to-all interaction and you have But yeah, we can actually talk about that later if you want. It's pretty easy to show. Okay. where was I? All right, so we have this overlap function. We have this order parameter. Right, and this is the saddle point equation. So this is the free energy. Now, to find the answer for the free energy, we need to assume some form of this order parameter. So we need to make an ansatz. We can first think about this as a replica symmetric case. So what does that mean? First of all, it means that the form of the QAB would be just dependent on one parameter, Q naught. So it's going to be Q naught plus some 1 minus Q naught delta AB. And if we do that, if we plug this back in here, if we plug it in back to the saddle point equation, what we get is just the simple form, and then we can solve for Q naught and finally get the answer for the free energy. However, people show that the solution is unstable, and we need to look for different solutions. So what does it mean to look for different solutions? It means that we need to do replica symmetry breaking. So before going there, just a quick connection between the spin glass order parameter, the one that we talked previously about, to QAB metrics. We can connect them using some expression with limits of replicas, of number of replicas. So I'm not going to show you how exactly it works. It actually works. Was worked out in the review I showed you previously. But yeah, so it works. So you can first the first moment of the QEA, the entered subsystem order parameter, is connected to the linear QAB, which is the matrix here. And more generally, you can actually find the kth moment of this order parameter. It is going to be connected to the kth moment of matrix QAB. So they are all very tightly connected with this weird limit of n going to 0. And Q1 is the self overlap that we called it. So this is just the actual order parameter of the system. Yeah, the sum is over all saddle points you can find. And the physical connection is due to the some Paris distribution function or probability distribution that's connected to this QAB matrix using the delta function. Yeah. Anyway, so more on that if you're interested, we can talk later. Interesting part is that if you have the replica symmetric case, so if your QAB is just one number, Q naught, then this probability distribution function just on average becomes delta function of Q minus Q naught. So essentially what it means is that your order parameter is Q naught, which is this ansatz of QAB, right? So they're just exactly the same. Okay, more on Q naught, more on the matrix QAB, just to give you a little bit more perspective of what's happening here. So this QAB, again, going back to this free energy, it's a huge matrix that on the diagonal has 1 because of the circle constraint, and then on the off diagonal, if we have a replica symmetric case, for example, this whole structure of diagonal structure is going to be Q naught. So this all the numbers are going to be Q naught. If we have, if we want to think about replica symmetry breaking, which means that we need to make an ansatz that would describe spin glass order. We need to modify this matrix, and we need to assume this block structure. So here we said that on these blocks there is Q1, and the size of this block is M, that eventually we will need to take to 0. And like all other numbers, you cannot. So now QAB depends on 2 parameters, Q naught and Q1. And this is called one-step replica symmetry breaking. So we had a replica symmetric case where everywhere was Q naught. Now we have Q naught and Q1, and this is called one-step replica symmetry breaking.
I'm sorry, is it what's the symmetry breaking? Is it just that we're assuming that the Q1s make the block, the Q1s and 1s make the block diagonal? Is that the symmetry breaking?
So we call this symmetry, we call it replica symmetry is QAB depending only on Q naught. So Q naught is everywhere.
Right.
Right.
So the fact that
Mhm.
the fact that the symmetry breaking is the fact that we're now implanting these Q1s on the block diagonal.
Exactly.
Ah, okay, cool.
Exactly. Exactly. We can do it many more times, as many times as we want, and make these blocks, with different Qs. So we can make it Q1, Q0, Q1, Q2, Q3, Q4, and so on and so forth. And that's called like n-step replica symmetry breaking. And eventually we can make it infinite step replica symmetry breaking. And the Parisi got the Nobel Prize for, explaining infinite step replica symmetry breaking solution of the SQ model. Yeah, so this is essentially based on this. So this matrix is called ultrametric, this whole structure. And yeah, so that's where it's coming from. Important to note here is that this Q naught is always less than Q1, and Q1 is always less than the diagonal value, or it's actually always less than 1. And Q naught, everything has to be greater than 0. So that's just how it works. Yeah, so now in one of these models, so this is kind of a typical structure of the order parameter for a model that we study in the paper. But essentially what happens if you take n to 0 limit, you obviously won't have the metric structure anymore. Instead, what you will have Q as a function of U, the parameter U. And by varying this U, Q will change. So this, the fact that Q grows with U, it means that there is infinite step replica symmetry breaking here. And then it saturates the same value, and then QEA is the final order parameter. So this is like a number. So how to map this to this? It's a little bit non-trivial, because again, like this structure does not exist in n to 0 limit, but one can at least intuitively think about it as going from the as far off diagonal as possible, and that will be U to 0. Closer to the diagonal, and then it's going to be U equals 1. So you go this way, and that's going to be your structure of Q of U. So the values that the closest to the diagonal are going to be your order parameters, and then off diagonal is going to be just some structure of this function.
Sorry,
okay,
is it distance from the diagonal?
Yeah, actually, yeah, it's yeah. Also, I'm a little bit struggling to understand it, but I think, like from discussions with people, I think it's kind of a Hamming distance from different replicas. Yep, I think I can think about it this way.
And I had maybe a tougher question.
Mm-hmm.
Why is a spin glass phase associated with replica symmetry breaking? So I can understand when you've got a model and you chose this high symmetric form for the order parameter. You can solve it, and you might worry that there might be some lower symmetry thing. But so why is a spin glass that symmetry breaking?
Why is the spin glass replica symmetry breaking? It's a great question. I don't know if. Well, okay, so there are a few answers here. So first of all, this is just the way people approach the problem, right? So replica symmetry breaking is a mathematical tool. So it's not necessarily like physics that actually, yeah. So that's a great question. That's why I was kind of trying to flesh this out, that there's the probability distribution of the actual order parameter that we can measure, and that's connected to the replica structure. But it's not very physical, because you have to take this like n to 0 limit.
But in the end, this bar is a physical thing. This P
in
bar,
the end, it is
for an infinite system, right?
Yeah, actually, yeah, exactly. For mean field spin glasses, exactly, we can measure
the isotropic case is where it's a delta function distribution, whereas the symmetry breaking case is where it's a non-delta. It's got a spread. Is that?
It's still a delta function, but it's just sum of delta functions. Yeah.
Sum of delta functions then gives you a spread, like it's not.
It doesn't give you a spread, exactly. That gives you like this non-trivial structure. Yeah. Mm-hmm.
And that's where that, and so the replica symmetry breaking is needed to get that non-trivial structure.
You can think about it this way. I think originally people just started trying to solve they were trying to solve this model, and they were like, okay, how do we do that? So then they just thought about this a replica trick, and then they're like, okay, let's replicate the system, and then it's actually solvable. And then, oh, like you can actually like write down the mean field theory of that, connect it to, you know, something. So I think it was like several steps towards the direction, but then they like found out the physical structure of it is actually connected to this probability distribution. So well, that's my understanding of this. Whether it's actually replica symmetry breaking or not, it's actually a very debatable question. So for finite size spin glasses, so what replica symmetry breaking assumes is that you have a landscape of you have energy landscape in equilibrium, and then you have many minima, and they all separated by infinite barriers. So that's essentially what it means. In finite size spin glasses, in finite systems, you don't have this infinite barriers anymore. So you have like finite barriers. And people don't think that it's going to be describable by replica symmetry breaking, but nobody knows actually whether it's replica symmetry breaking or not.
Yeah. There's an order of limits there as you make the system size longer and you have time to do things.
Yeah, exactly.
You don't know exactly what happens.
Exactly.
One possibility is the barriers grow so fast that you might call it.
You can make it replica symmetry.
The other possibility is they don't grow that fast.
And
always sort of escape, and you don't break the symmetry.
Exactly. So there is the question that we're actually asking right now is imagine that you have out of equilibrium scenario. So you just initialize the system with something, and as the plot I showed you, access the outer correlation function. It does freeze, right? You don't need any replica symmetry breaking structure, no replicas at all. It's just you just do the simulation. But then why does it freeze? Like why does it saturate to some value? Like one would think that there's probably some connection to replica symmetry breaking if replica symmetry breaking is real. So yeah, that's sort of a question people asking, like how is that time evolution related to the replica symmetry breaking structure in equilibrium? Because it should be somehow connected if it's true. All right. So yeah, this is the order parameter. Are there any more questions? Oh wow, 11:05 already. Okay, let me just briefly sketch. This is our work finally. I'll just sketch brief results of what we've done. So now we pretty much talked about classical spin glasses. Quantum spin glasses are kind of similar, but you just add some transverse field. So that's what makes it quantum. So again, you have Ising spin glass now. You have ZI-ZJ interaction, and there's GIJ's auto random Gaussian distribution. And you also have longitudinal field. So background here is that this model, just the quantum Ising spin glass, was studied a lot. Now, nobody really cared about adding longitudinal field, but we did because it's very much tightly connected to the physical realization of these systems in quantum simulators. So that's the model that we wanted to study. And then we're asking
the integrability. Is that right, or is it already non-integrable with the random coupling?
It's non-integrable, yeah. And plus there's just no symmetries left, right? So you broke all the symmetries. So yeah, yeah. So we studied this model, and what we're asking is, what is the phase diagram of this model? In other words, how is there any spin glass phase in this model? And apparently there is. So the bilocal feeds that I told you about now. So first, what is the difference between classical and quantum spin glass? Remember this QAB matrix now becomes time dependent. So that's for a quantum case. Time evolution is crucial here. And in equilibrium, this two-time dependent bilocal fields become local, essentially. They just depend on time difference in equilibrium. So for this QAB, we again make the ansatz. That ultrametric is just essentially written here. And we make it like replica symmetry breaking ansatz. So this QAB is QAB is the ultrametric here, and this is the diagonal form in the Matsudaira space. And the structure of this QAB is the following. So when your H is non-zero, you have this plateau of this Q. Then you have infinite step replica symmetry breaking, and then it saturates to some equilibrium value, QEA. All right, so the main result that we found is in this specific model, first of all, there is a spin glass solution, there is replica symmetry breaking solution, and also the spectral functions in this phase, they are all gapless. So that's interesting because there's no gap, even at non-zero field. Now this X where there is this cusp happening is called the breakpoint, and it's an important value because it depends on the temperature. So that will dictate like whether you go to lower temperatures where the structure becomes more like order parameter, whether if it's high temperatures, in order to reach the order parameter, your infinite step replica symmetry breaking it occupies a lot. In this QH, we also can find an analytical form of. So it depends on this on the longitudinal field. Okay, the phase diagrams, the following. So we fix the temperature. It's pretty small, but it's non-zero. That's important. This H is the longitudinal field, and R is just the parameter in the Landau theory. So yeah, first of all, we study Landau theory of this model. So this R is the parameter in Landau theory that like makes you to go from one phase to another phase. And we measure the gap in this case, and we see that the model becomes gapless in quite a large regime, and then gap grows, right? And this is the actual phase diagram. So measuring the order parameter, what happens? So actually, I think this is based on free energies. So whichever free energy dominates, that's the one that gives you the phase, corresponding phase. So H again is the longitudinal field, and R is the something related to transverse field. And you have RSB phase and you have RS phase, which is this replica symmetric phase. This is a replica symmetry breaking phase.
I guess a quick question.
Yeah.
The shape of the line that separates RSB from the RS.
Yeah.
Different than the shape of the lines that were for the gap.
Oh yeah, this is just a different parameters. Sorry.
But like like I was expecting, I don't know if you can see where like at R, well.
Yeah, I know what you're talking about. So
bending one way, curving one.
I know, yeah.
Whereas the other one is curving the other way. So is that
H is a different order parameter, she said, yeah.
No, H is the longitudinal field.
Oh, it's still the
H
same parameter for both?
It's field, yes. H is the same.
Oh.
R is also the same, but here we have another parameter in the model. So in the Landau-Ginzburg theory, you have also the quartic term, and you have a parameter there, which is called Y. And this is just a different parameters of Y. Yeah. So,
I see.
No, there was a shape of like that. Sorry, I should have changed it, but yeah, you're right.
I just want to mention in 4 minutes, I think my Zoom is going to get upset with me.
Awesome. Yeah, I'll just mention one last result and we can right. So one last result is we have another model which is called rotor model, P rotor model, and it's quantum, also in the longitudinal field. And we study this model, and what we get is also the same thing. We have the phase diagram. We have RSB phase. We have RS phase. And the whole RSB phase will have gapless solution. So there's no gap here. Yeah, anyway, so conclusion. We found the replica symmetry breaking phase, which is the spin glass phase, in quantum Ising spin glass and quantum P rotor model. The spectral functions we also found gapless in the RSB phase in both models. And the phase diagrams also, very well described for both models. And for the next, I think we want to do out of equilibrium dynamics in RSB phase somehow. And that is necessary in order to do experimental realizations of spin glasses. and how to more strictly connect the quantum optimization problem to the spin glass problem. So what do we need to measure? What do we need to study in order to answer these questions that people asking about the optimization problem? All right, I'm done.
Right, thank you.
Sorry, I went over time.
I don't know. We asked a lot of questions. You're over time only because we asked lots of questions. So I don't know. Can I maybe, because I have like 2 minutes, but does anybody have any question, any burning question, additional burning questions? Can I ask a quick question? So how important was H, little h, in your quantum?
Yeah.
model? Was it crucial for getting this RSP phase or not?
So this is crucial because without H, the models were already studied. So H would makes it the new model. Essentially.
Right.
So that for us, it's very crucial.
We got 5 more minutes. We got 5 more minutes. We're not that rushed. So I just gotta mess.
And it's interesting because when you add H, you essentially break all the symmetries in the model. And one would think that there shouldn't be any ordering, right? There shouldn't be any spin glass order at all. But we do find it, and it's in actually a huge range of parameters. And
Could you show where H shows up in the formulas again?
oh yeah, yeah. So H in this model is right here. But this kind of weird model. So here's the H. So this is ZG, it's X, and yeah.
So previous to your study, without H, the results were already known for this model.
Exactly. Yeah.
And there they still get the replica symmetry breaking, but it's
yes, exactly. Yeah. So Beer actually studied in, I think, in '92. He also did the Landau-Ginzburg theory of this model and without H, and he proposed that if you add H, then you won't end up with any replica symmetry breaking phase. But then we redid his analysis and he actually did. So Sabir is arguing with himself. Yeah, but anyway, yeah, we took into account all of it. And
I have a very beginner question. Could you explain the relevance of having the gapless phase versus the gapped phase?
Relevance?
Yeah, like why, like what do you, I guess what do you mean by gapped?
Energy gap, I guess, right?
Yeah, exactly. Yeah. Just the spectral functions. Yeah. When you couple it to excitations, you have like a finite energy thing to apply to go to this state.
So what does the gapless phase mean for spin glasses? Like what is the relevance of the gapless phase to spin glasses? Does it have to do with what does it have to do with the superconductivity graph that you showed us in the beginning, or?
Well, I mean, that's kind of an application, right? So just the general like gapless phases, they're pretty cool because you can apply any amount of like excitation, and you will end up with like infinite amount of, you can apply a little bit of as a quench, for example, and you have like infinite amount of excitations, right? So that's just like by itself is a cool physics, like spin liquid, for example, so like gapless and stuff.
Yeah, I guess for reference, if you consider the clean case, right?
Yeah.
There's one gapless point, which is the phase transition between the ordered phase and the disordered phase, and everywhere else gapped, right? So here, spin glass, we're getting a whole gapless phase, and you don't even know how long. I don't know. This is a Landau theory, but you don't know how. It looks like it gets gapless forever, going to the left, but it's a very
it does end somewhere. It's just not shown here. But yeah.
But yeah, so it's a whole phase rather than getting a
point.
Yeah. Okay, that makes a lot of sense. Okay, cool.
Yeah. That's
all right. How about we call this to a close? Thank you very much for joining us. It was I think I learned a lot, so I greatly appreciated it.
Thank you so much. And yeah, if you have any questions, you can email me.
Sure.
And, yeah.
Or people.
Thank you very much.
Comments on YouTube. There could be comments there. You can probably put.
Oh, you can do that.
All right. Yeah. All
All
right.
right. Thank you so
Thank
much.
you, Maria.
Thank you.
Yeah, you're welcome. Bye. Nice meeting you.